waiting for a while, and now finally we are ready to go. All right, so application 72 laws. Car versus SUV, both of them are traveling at 60 miles per hour. Both of them will lock their brakes. They will lock up their brakes. Imagine that both will skid to a stop. So both of them are skidding to a stop. So the question is, which one, if any, will come to a stop sooner? Okay, so we had this discussion, and what'd you guys say? Most of you guys said, yeah, most of you guys, it's just not most of you, all of you guys said the car is going to come to a stop sooner. Okay, so when asked, you guys said, oh, because it's less inertia, right? Less mass, less inertia. So which means that it's going to take less force for it to come to a stop. And on the same lines,
there is no question four-wheel drive vehicles offer better traction in the snow and can get through bad weather conditions when other cars cannot. But there is one thing, they do not necessarily do better than any other vehicle. What is the biggest mistake that SUV drivers make in bad weather?
Underestimating the stopping distance.
Some motorists assume since they have four-wheel drive, their SUV will stop quicker. Can an SUV stop better in bad conditions than, say, a Honda Accord?
Absolutely not. In fact, even on dry pavement, an SUV takes longer to stop than an ordinary car would.
Because of the weight of the vehicle, does it take longer for it to stop?
Oh, yes, absolutely. The heavier the vehicle, the longer it takes to stop.
Okay, so that's precisely what you guys said, and this guy agrees with you. Okay, so the next observation that I gave you, you got two cars. In every single imaginable way, they're identical. Except one of them is going to have an anti-lock brake system. The other one is not going to. All right, so the car without the anti-lock brake system is going to skid to a stop. And the car with the anti-lock brake system is going to come to a stop without skidding. So the question is, which one is going to come to a stop sooner? All right, most of you guys said the car without the anti-lock brake system is going to lag behind. Most of you guys thought that the skidding car would be coming to a stop sooner, right? That's what you said. Car versus a train, which one comes to a stop sooner? Just about every single person said the car is going to come to a stop sooner. When asked, you guys said, once again, it's the same as the car versus an SUV. Car is lighter, less inertia, it'll come to a stop sooner because of it.
And in case you think a speeding train could simply stop if you were on the tracks in front of it, consider this. A fully loaded freight going 60 miles an hour might take 1.5 miles to come to a halt after the brakes are applied. That's the length of 25 football fields.
That number even accurate. Most of you guys said, yeah, it sounds right. All right, so according to Newton's second law, net force is what causes acceleration, right? So whenever we walk, what happens? You speed up at will, you slow down at will, you change direction at will. So if that's the case, where does the external force come from? Okay, so the only external forces can cause you to accelerate. You cannot lift yourself up by pulling yourself in the upward direction, while pulling up on your nose or the other arm. It's simply not going to happen, right? You cannot lift yourself up by using an internal force. So where does the external force come from? Some of you guys said that, oh, it comes from the ground, which is correct. All right, only through friction you apply that force on the ground in the opposite direction, in the backward direction. In turn, the ground through friction is going to apply the same force back on you in the forward direction. That's it. So the action force is acting on the ground. The reaction force is going to act on you, right? So in that way, at will, you're able to speed up, slow down, or change direction through friction. So through friction, we get around. If we weren't for frictional force, none of us would be here today, guys. And you know what I'm talking about. I'm still talking about walking. All right, so you can't get around without the frictional force. It's an impossibility. So speaking of friction,
how it works. Look at this video from ITT Automotive, a company that manufactures ABS systems. First, watch what can happen without ABS. Then, with ABS, the driver stops in time and maintains control of the car.
All right, so
how it works. First, watch what
same driver, same car,
can happen with
same speed. Everything is identical.
Without ABS.
Without the anti-lock brake system, it's tough to control the car.
Then, with
the anti-lock brake system, once again, it's identical speeds.
The driver stops in time.
Not only do you control the car better,
and maintains control.
Also, this car will come to a stop sooner.
Control of the car.
How's that possible?
Of how it.
This becomes possible because the car with the anti-lock brake system is experiencing more force, which means that the frictional force, the force of friction that it's experiencing, is going to be larger than a skidding car, in essence. Skidding car is going to experience less friction. Rolling car, the car comes to a stop without skidding, is going to experience more friction. How is that possible? Now, for us to be able to answer that question, we need to know something about friction. So what are the contributing factors to friction? What contributes? How about the size? Does it matter?
Yeah, those first ice boats had a lot of speed, but not a whole lot of control. Yeah, with the blades sitting there, he couldn't steer around the ice fishing holes. Oh, geez, learn the hard way. Wider is better.
With its speed-sensitive steering technology, the White Track Grand Prix gives you precise cornering and control, even at a good flip.
You betcha. Better.
Wider is better. The White Track Grand Prix by Pontiac.
All right, so when it comes to friction, does the size matter? What do you guys think? Does the size matter? When I'm talking about the size, I'm talking about the size of the surface area of contact. All right, so what do you guys think? Does the size matter when it comes to friction?
Yes.
Okay, I'm just I'm waiting because I got too many windows open.
So,
Okay, I found it.
does it apply to, are we saying like the tires are wider or the body of the car is wider? Because I think the tires would matter, but the car might not.
Okay, Jack, that's exactly right. I'm talking about the size of the area contact, right? So we're talking about the size of the tires. Here's 5 points for the clarification, and also give 5 points for saying that the size is going to matter. Okay, guys, so surface friction is what we're dealing with, right? Surface friction. So our topic is surface friction. Okay, so what I'm going to do, we will use the lowercase f for surface friction. All right, so in terms of the surface friction, let's come up with 3 contributing factors. The first one is going to be the area. All right, so let's call it the surface area contact. All right, so surface area contact. All right, so this is going to be our surface area contact. Let me just do this. So this is your A, so this is your A, right? Okay, that's good. All right, so will it matter? Most of you guys will agree that A, of course, is going to matter. The larger the surface area contact is, the more the friction is going to be. All right, what's the second contributing factor that we could come up with? The second one that we discussed is maybe the nature of surface, right? Okay, so which one is going to give you more traction? Is it the ice or is it the carpet? You know that the carpet is going to give you more traction, right? So the nature of surface is going to be denoted by this letter mu. All right, so this is a Greek letter mu. All right, so we'll call it the nature of surface maybe. All right, that's the commonsensical way of looking at it. Let's call it the traction number. Traction number. The technical term is the coefficient of friction. All right, so the coefficient means friction. Friction. Coefficient means it's a number. When I say traction number, it means the friction number. So instead of saying number, we say coefficient. The reason why we do that, because when you say coefficient, all of a sudden the people who are not physicists cannot contribute because you don't know what's going on. It's called jargon, the scientific jargon. You just want to keep the people who are not within the field outside of the conversation. So this is the coefficient of friction. All right, so area. All right, so this is the surface area contact. Mu is the coefficient of friction. It's an experimental number. So this thing is an experimental number. All right, so this is an experimental number. Nice. So you just kind of have to measure it. And so is an example of it. The coefficient of friction for ice is going to be larger than the coefficient of friction of carpet. Okay, yeah, only in my dreams. Okay, so the coefficient of friction for ice is going to be smaller than the coefficient of friction for carpet. All right, so the traction that you get from ice is going to be less than the traction you get from carpet. All right, now it makes sense. All right, the third contributing factor for friction that we can think of, I don't know how well I'm going to be able to do this, but let's do it anyway. Okay, guys, listen for this. Okay, so I got the piece of paper. So what I'm going to do with this is I'm going to generate a little bit of friction. All right, I need to be able to see this. So let me stop sharing and get out of here. Okay, I need you guys to be able to see this. Okay, so cool. All right, so you can hear this, right? Okay, so you hear this. So what's generating the sound is friction. There's no question about it. All right, so notice that it's fine. And then when I press on it, obviously by pressing on it, I increase the friction because the sound is amplified, right? Okay, if I press on it further, notice that it doesn't move. Okay, so when it easily moves, and you can hear the friction. Press on it a little bit, and then it makes more noise because the friction goes up. And if I press on it harder, it doesn't move. Okay, so by pressing on it harder, what is it that I'm changing? Am I changing the weight? Okay, very good. By pressing on it, okay, my question is, does the weight matter in terms of friction? Yes or no?
Yes.
Yeah.
Yes.
It doesn't make it much sound. When I press on it a little bit, friction goes up. I press on it more, and obviously friction goes up further. Okay, so let's provide a clarification for this one. So by pressing on it, am I changing its weight? The answer to that question is no, it still weighs the same. Okay, by pressing on it, what is it that I'm changing? I'm changing the normal force. It's apparent weight, right? Okay, in physics, everything is carefully defined like that. So by pressing on it, I change the load on it in essence. So which means that I'm changing the reaction force, which means that I'm changing the normal force. By pressing on it, I end up changing the normal force or apparent weight. So the third contributing factor that we can come up with, by pressing on something, I'm changing its apparent weight. How much something appears to weigh is going to change its friction. All right, so those are the three contributing factors. Okay, so here's a question for you. If you had to pick one, all right, so this is the apparent weight. Now, your common sense will argue that all three are contributing factors. There's no question about it. That's common sense, okay? Physics will say one of them is not a contributing factor, okay? So physics will say only 2 out of 3. So you got 3 possible contributing factors. Physics will say only 2 out of 3 will be contributing factors. So if you had to get rid of one, which one would you get rid of? Which one would you say is not going to contribute to friction? Okay, put it in the chat. I'm just curious what you guys think. If you're forced to get rid of one of them, which one would you get rid of? Just give me an idea. So I want to know what it is that you guys are willing to sacrifice from your common sense. Which one you think may not be a contributing factor? Okay. All right. So Lucia says, Lucia wants to get rid of the nature of surface, the coefficient of friction. Okay. What else? Okay. Give yourself 5 points for committing to one of them. Jack says, I'm going to get rid of the surface area contact. All right. So, okay. Most of you guys are willing to get rid of size. You're thinking that size probably doesn't matter. Okay. Not bad. All right. All right. Every single person who said something, if you had to get rid of, I noticed that most of you guys are willing to get rid of the size of the surface area contact. Okay. I'll give yourselves 5 points for that. Let's check to see what physics says. Okay. So does the size matter? That's what we're going to look at. Okay. Nature of surface is going to matter. Obviously, you get more traction from carpet than ice. No one argues that.
They are closed now for cleanup.
Not only the nature of surface will matter, but also
and they're going to remain
the conditions of the surface is going to matter.
Closed until the Thursday morning rush hour. But it is ice that is the problem in Little Rock, Arkansas. Dangerous driving there. The ice storm is also causing problems at airports in the Southwest, which is also causing problems, a few, at O'Hare tonight.
Same road. When it's dry, tons of friction. When it's wet, friction goes down a little bit. When it's icy, forget it.
She'll have the night.
All right, so coefficient of friction. All right, these are the traction numbers, experimental traction numbers. I want you to focus on rubber on concrete for a dry surface versus the wet. All right, as soon as the surface goes from being dry to wet, what happens? The traction number changes. It goes down. It diminishes. All right, so the coefficient of friction is a traction number.
2 people, 2 accounts, 2 conclusions. In the science of crash investigation, the unpredictable element is the human factor. The unpredictable.
You got 4 tires. 2 of them are on asphalt. 2 of them are on grass. Asphalt is going to give you a lot of traction. Grass won't. So it's going to be virtually impossible to control this car.
Is the human factor.
Hence the cause. Hence the cause for this accident. All right. So the second contributing factor is the weight. Okay. So the weight is going to generate an apparent weight. I've just done a small demonstration. Obviously, you could tell that by increasing the weight, the downward force, push in the downward direction, we were able to change the apparent weight, right? So when you increase the apparent weight, what happens? The friction goes up. The only thing that doesn't matter, and this is an experimental fact, the size doesn't matter. The size of the surface area contact is not going to matter. All right, so the size of the surface area contact is not going to matter. It's just an experimental fact. So what happens when you actually increase the size? The pressure is going to go down. All right, so which means that the downward force is going to get distributed onto a larger surface area. So which means that it's not going to change the friction. So the friction is going to remain the same. So the size of the surface area is not going to matter. Okay, so this is kind of a very counterintuitive statement. All right, your mind is not going to catch up with it right away because your mind is going to disagree. All right, so pick out the best answer and then put it in the chat. Wow. All right, give yourself 5 points. Your mind is going to disagree with it, but evidently you guys are doing really well. All right, give yourself 5 points. That's correct. Okay. Your mind is still going to argue that the size of the surface area contact is going to matter. Reality of it is it's not going to matter. So here's what I'm going to do. I'm just going to go in here and I'm going to say this is not going to matter. All right, it's an experimental fact. So let's just cross this out. So the size is not going to matter. So what's going to matter is the coefficient of friction is going to matter and the normal force is going to matter. So this is going to give us a formula. The formula is going to look like this. Frictional force is going to be directly proportional to the amount of traction that you get and the apparent weight. That's it. All right, so that's the formula. Frictional force formula. So the size of the surface area contact is not going to matter.